go. All right, well, cool. Well, thanks everybody for having me. I'm Chase Straw. I'm an assistant professor of turfgrass science at Texas A&M University. And today I'm going to talk a little bit about precision turfgrass management, some current trends that are happening in the industry, and then some future applications. And yeah, that was a really good presentation by Ken. I learn something every time I hear him talk, and I look forward to continuing to work with him on some of the research that I'll be talking about today. So precision turfgrass management, it's really based around this whole concept of managing variability. And I'm assuming that most of the people on here are golf course superintendents. And as you all probably know, there's a lot of changes that happen throughout your course. Spatially on a day-to-day, on a daily basis, and then temporally on a day-to-day, week-to-week, or even year-to-year basis. And this variability is, it's inevitable. All turfgrass environments are going to have some type of changes throughout. So just a really simplified example would be just one fairway. As we can see here, there's probably some kind of cart traffic issues potentially happening in the lower part of the fairway, some shade issues probably throughout the day, kind of in the middle there. In approach areas, sometimes those are different soil types than the fairways themselves. So all of these different things basically create micro environments for growing your turf. And the question really that kind of stems from that concept, and especially whenever you extrapolate across an entire golf course and the changes that could happen across such a large area, are blanket management applications really necessary? Or can we target specific areas based on whether it be environmental conditions or just the use of the area, and have a more targeted management approach? So just a real quick summary. I've used this graph for years, so if anybody's ever seen any of my presentations, I typically always have it. But I think it's a really good just example of what exactly precision turfgrass management is and what our goal is. On the y-axis here, we have everything we desire: turf quality, playability, uniformity, and obviously we want that to be high. And then on the x-axis here on the bottom, we have everything that you have to put into your turf area to achieve that high quality, playability, uniformity: your resource use, costs, labor, and then the environmental impact for all of that. The zone of normal operation today, I would say we are kind of trending more towards at least the moderate input use with some of the technologies that are currently available. But the zone of normal operation is really kind of in this medium to high input. It's the best we can do with the info we have. It's safe, it's predictable, it's what we've always done. With precision turf management, it's really trying to move that zone of normal operation over here to this plateau area where we're still achieving all of the things that we desire when managing turf, but using substantially less resources, and most importantly, less environmental impact. Now to make this move, we need data, we need new technologies like Ken talked about in the last presentation. And honestly, we need to take a little bit of risk, especially initially. There's a lot of risk that can go into some of the things that I'm going to talk about today, and some of these newer concepts that surround precision turf management. But as the research continues to come out, I think we'll see a significant reduction in inputs while still maintaining that high desired turf product. So today I'm going to talk a little bit about data sampling devices and technologies that you can use for precision turf management. Precision turf management's really, it's a big umbrella, and I'm only going to talk about a couple things kind of under that umbrella that I'm specifically working on. Precision turf management is actually more than just site-specific management. I think it's just a more data-driven approach, and there's a lot of data-driven approaches to some of the things that we do in the turfgrass industry that I won't talk about today. But I'm going to focus primarily on the site-specific applications of precision turf management, particularly surrounding soil moisture and NDVI, which I'll talk about here in a minute. And then spatial maps and how to interpret them, and how to collect the data to create the spatial maps, and then potentially use them for something meaningful from a management standpoint. And then specific precision turfgrass management applications. I've worked a lot in irrigation on golf courses, and I'll talk about that today. But I've also began last year dabbling in a little bit of other concepts of precision turf management for golf courses. I also do a lot of work with sports fields, and some of them apply a little bit to golf courses, some of them don't, but I still have a few sports field slides in here too, just to kind of show you as an industry where we're going with this, not only in golf, but also in a sports field application. All right, so most of you all are probably familiar with this device or something similar to this device. It's just a soil moisture meter. This is a TDR 300. It measures volumetric water content, which is just relatively speaking the volume of water to the volume of soil. It's an indirect method of soil moisture content. So you simply stick these stainless steel tines into the ground, you push a button on the user interface, and you get your percent volumetric water content. I would guess that the vast majority of people, of superintendents or assistant superintendents or just golf course staff that's working right now that is in this presentation, they primarily use it on putting greens. I would assume that very rarely do you venture out into the fairways. Maybe you have certain spots that you do fairways, but you probably don't sample as intensely within fairways. And I'm going to talk a little bit about expanding your data collection to fairways later, because there's a potential for significant water savings if you use some of these types of data in those much larger areas. So these are probably, well, the two on the left here are probably the most common devices, the TDR, some version of the TDR. This one here in this picture is the 350, the Pogo there in the middle. And then one of the probably less used devices is a Campbell Scientific HydroSense. All three of these devices are equipped with GPS. And GPS is becoming obviously very, very important. As you all took away from Ken's presentation to do these site-specific applications or collect data in specific locations, so that we know where we're at when we're doing something. And in this case, when we go out to collect data with these devices, we know the latitude and the longitude location of where we collect the data point, which can be later used for further analysis. And then the second variable that I'm going to focus on with this presentation is NDVI. NDVI is Normalized Difference Vegetation Index. It's a spectral reflectance measurement of the turf. So it measures the reflectance of typically wavelengths in the near, infrared, and red spectrum. The red spectrum particularly is important because that is where chlorophyll absorbs red light. So by measuring these two wavelengths, we can plug it into this NDVI equation, typically get a number in turf between 0 and 1. In theory, it's also -1 to 1, but in turf, it's going to be 0 to 1, and you'll likely never get that close to 0. But that's just an indication. The number closer to 1, if you get a number closer to 1, that means a higher turf quality, and as you get closer to 0, you have a lower turf quality. There's other terms for this. Turfgrass vigor is another one, but it considers the greenness of the turf, the density of the turf, and just spits out an objective number that you could use to create some kind of threshold to trigger some kind of management decision. So there's all sorts of NDVI devices. This is a handheld version, also made by Field Scout. You just point it at the ground, you pull a trigger, and it'll measure those reflectances and then automatically plug it into the equation to give you your NDVI. So just a real quick example, just a visual of what exactly we're measuring here. A healthy turf is going to absorb more red light, so that means they're going to reflect less red light because they're absorbing it and it has more chlorophyll, whereas a stressed one is going to reflect more red light. And whenever you plug these numbers into the NDVI equation here, you get this number between 0 and 1, with the number closest to 1, a healthier turf. So NDVI is probably the most common now, but there's also a NDRE, which is Normalized Difference Red Edge Index. And there's even a couple other newer indexes that are coming out that measure slightly different wavelengths, but are also just some indication of turf grass quality. NDRE is probably the other most common one in turf, and it's becoming more and more common. And there's some research out there that says it might be more applicable to turf, but nonetheless, NDVI is still pretty common, and what I've used primarily up until this point, although I do plan on using NDRE in the future. So drones, another option for NDVI. If anybody's flying a drone, typically you have some kind of multispectral camera where you can get just a typical image of your course, and then also RGB, and then near infrared, so that you can use those red and the near infrared wavelengths to calculate the NDVI or NDRE, even in some cases. So anybody who's flying a drone is likely familiar with some kind of spectral reflectance. Also, you can measure thermal. I think I have an image of a sports field later for thermal, but I'm not going to talk too much about that today. All right, so those are the two main ones. Main variables I'm going to talk about. I will mention a couple others kind of sprinkled throughout the rest of the presentation. But how can we take this data and better visualize the variability, which is what we're most interested in precision turf management? Well, we need GPS, which a lot of the devices now have. Even the handheld NDVI meter has a GPS. We need some kind of data, which these devices that I've shown have. And then we need a GIS or some kind of software to manage or analyze the spatial data that we have. And that's called a geographic information system. So the way that we would kind of handle this whole data collection process is we could go out into whatever area that we're interested in collecting data, collect a lot of data points. In this particular case on the fairway, we have a soil moisture sensor here, and then Will, this gentleman here, is collecting NDVI with a handheld NDVI meter that you have to put at the surface. And he's walked the fairway and collected about 105 data points. So each one of these data points was collected with that HydroSense soil moisture device. Each one of the data points has a latitude and a longitude location attached to it, as well as whatever data that was collected by that device. So if you're using a TDR 350 or even a POGO, then you could have other data like EC attached to these individual data points. And then the GPS obviously records the latitude and longitude, and that's how you get these data points. So whenever you input it into a GIS software, they could show up like this. Now, there's a lot of things that you can do to create the boundaries of your fairways. One is one that Ken touched on. You could drive your GPS sprayer around your boundary and get it that way. Or you can just simply draw it in the GIS software. And then it'll just show up for you, and you can have it geolocated to do different types of analyses in the software. So there's various ways to create a boundary, but once you have a boundary, once you have your data, then you can start doing different types of analyses. And probably the most important analysis, and the one that I'm going to talk about the most, is creating these spatial maps. So this is a really simple map of soil moisture created from those 105 data points. Actually, let me go back to the data collection. So 105 data points, that sounds like a lot. Once you have a system down, and once you've done it once, twice, could take maybe, for a typical par 4 or par 5 fairway, it could take you anywhere from 30 to 45 minutes. So yes, it is time consuming, but it's not as daunting as you would think. An entire golf course, I've walked and collected on average 80 to 120 data points for all par 4 and par 5 fairways, and it took me a full 8-hour day to do it. So it does take some time. Another advantage of using these handheld devices with the GPS is that you can go around to all of your irrigation heads and utilize the GPS in that too. Or if you have a GPS sprayer, I'm sure you could do it with that too, and geo-reference where your irrigation heads are, so that you'll have them for whenever you do any kind of analysis like this to create a spatial map. So back to the map. So this is a soil moisture map. I'm going to show a lot of these. The way that you interpret these is the darker areas are the higher soil moisture or the volumetric water content. And then as they progress down to these lighter blue areas, these are the driest areas in the fairway or the lowest percent volumetric water content. And there's a lot really that you can take away from these maps. If you know your fairway, then obviously some of these things might stand out to you, or you might have recognized just based on your experience. Just looking at this particular fairway, we know that we kind of have this dip here in the middle, and that shows up as a wet area. So maybe that's where all your water goes. Up here near the approach is really dry. So maybe you have a little bit more sand, and it's showing a little bit less volumetric water content because it can't hold the same amount of water as other parts of the fairway. So some of these things you might be able to easily determine or just know based on your experience, but then there's some other things that could also pop up. In particular, this area here, kind of at the bottom of the fairway, this strange circle. Maybe you have a malfunctioning irrigation head or an irrigation leak that you couldn't really see if you didn't have the data. You might eventually see it, but the maps really highlight any kind of current issue going on. So as far as mapping software, these are becoming more, I feel like newer ones are popping up pretty frequently. There's a lot of options. Some you pay for, some you don't pay for. Most of the devices, especially the ones that I've shown already with respect to the soil moisture, they have a software where they'll analyze the data for you. They'll spit out a map for you. Anybody who's involved in Twitter has seen maps from Pogo or in lesser cases Field Scout with their software. So there is that option. Those options come with the subscription fee, and if you're able to pay for the subscription fee, then that's obviously the easiest way to get the maps. But if you can't pay for the subscription fee, there are a lot of free options. I think all of these that are on this image are free except for ArcGIS. ArcGIS is one that's used pretty common in a research setting. RStudio here is a data analysis software, so unless you know how to code, I wouldn't recommend doing that. QGIS is one that I use, and I'll talk about here later on. And then these other three, GeoDA, this is actually called Grass GIS, and then Saga, are all free open source softwares that you can download and do some of the things that I'm going to talk about on your own if you just did a little bit of homework watching YouTube videos and whatnot. So those are a lot of the handheld technologies. There's also a lot of mobile sensor technologies out there. I wouldn't say they're widely available, but they are out there. One that I've used a lot, and I'll talk a little bit in more detail, is the Toro Precision Sense 6000, which is this device here on the top left. It's a mobile multi-sensor device, and I'll show that here in a minute. The Varus machine here that measures EC. This is a mobile Clegg hammer, so it's more geared towards sports fields, but used to measure surface hardness. And then ground penetrating radar, which I know the next presenter will be talking about. So all of these are devices that are out there. I don't know if if I would consider them widely available right now, but nonetheless, they are out there. So this is we just got one of these in Texas, so I do a lot of sports field research, so I'm kind of excited about it. This is the mobile Clegg that measures surface hardness. We'll use this for a lot of the athlete surface interaction research I do, and also some of the precision turf management research that I'll do on sports fields. So this is basically a missile. It has a rotating arm. The device has a rotating arm, and there's a missile with an accelerometer that is going to hit the surface here and measure the impact once it hits the surface to determine surface hardness. So you can get a lot of data in a short period of time with that device. The Precision Sense 6000 is one that I've used a lot on golf courses. It's a multi-sensor device. It measures soil moisture and then also NDVI. So this is another option to collect NDVI. And I know there's some work out of Dr. Cruiser's program at Nebraska with some of these proximal green seeker sensors on the back of mowers. This is kind of the same concept on the back of the Precision Sense here, and there's two. So as you're driving this device along, you can collect rapid NDVI or NDRE data to give you some kind of indication of turf quality to go along with your soil moisture. And then in this case, this also measures soil salinity and compaction. So compaction is penetration resistance, so the amount of force that it takes for these two stainless steel tines to enter the surface. So this is the sampling head. It has the similar sensor to the soil moisture sensors that are in the handheld devices, a little bit different, but I won't go into detail on that. And then it has a load cell sensor to measure the amount of force that it takes to penetrate. That'll give you the compaction reading, and then it also measures salinity. And then while it's collecting all of this data, it has this GPS here that every time these stainless steel tines go into the ground, you're going to get a latitude and a longitude location, and same for the NDVI. So here's an image of that being driven along a fairway. You have to drive both of these devices at 2 miles per hour. So in the case of these particular Toro devices, when we talk about time, it takes about 30 to 45 minutes to walk a fairway, and you get roughly 100 data points. With this, it takes about 30 to 45 minutes to drive a fairway back and forth, but you get hundreds and hundreds of data points. So it's really just kind of that trade-off of what are you using the data for? Is it valuable to have hundreds and hundreds of data points given whatever you're trying to do with the data? Or can you just simply walk it and get your 100 data points and still have a useful map? So it really just depends on what you want the data for. Drones, admittedly, I've been involved with drone projects, but I have not been, I have not done a lot of drone work myself. So I don't have a lot of research to show. But nonetheless, I have dabbled in it enough to be somewhat knowledgeable in it. A lot of the work that I do is on the ground. My slides have frozen, there we go. But typically a drone, the way that they work is you fly your course, it takes frequent images, and then you use some kind of software to stitch them together to create what's called an orthomosaic, which is just this compiled image. So anybody who's ever had a drone fly at their course, you'll notice that the edges are kind of rigid of your image. It's because they've stitched together several images to create the one, which in itself can introduce some error, some accuracy error, but nonetheless, it's still somewhat accurate. And then you can use ground control points to geolocate and be sure geographically your images are where they're supposed to be. So just an example on a football field. This is a football field in Georgia where we flew a drone. This is just the visible image from that drone picture. This is the NDVI. So I like to show this image because I have issues with some NDVI images that get skewed. And in this particular case, our interest is the football field, but NDVI has also picked up these bushes and even parts of the road. And anybody who's had NDVI flown at their course, your bunker or your cart path, those can kind of skew your data and your images, which is going to make it a little bit more difficult to interpret. Now, in this case, it's just a football field, so you would assume that you know, maybe the sideline where the players stand or the middle of the field is going to be the worst. But if you have an entire golf course, you really want to be honed in on your fairways and your greens or whatever, your managed turf, so that you can really identify deficient areas a little bit better than that. So the scale of your data is really important. And I think we are getting a little bit better, and some of the drone companies are getting a little bit better at accounting for or trying to remove some of the noise and focusing a little bit more about on the areas that we're most interested in. Thermal, I'm not going to talk a lot about thermal, but if anybody is using thermal and or thinking about using thermal, I just wanted to highlight a couple limitations of it. One is shade. So you can see in this thermal image that the light pole, the shade from the light pole has shown up. There's an indoor facility next to this outdoor one, and this is the shadow from that facility. And then they had just recently relayed sod on this part of the football field, and they were blowing fans because it was really wet and they were getting ready to practice. And even the wind had influenced the thermal images. So thermal can be a little bit finicky depending on the time of day, and then also just the environment, whatever you're taking an image from. And then another option to collect data besides the handheld and the drones are satellites. So as we keep getting higher and higher above the ground, we lose a little bit more, in some cases, a lot more resolution and a lot more detail. So we're a little bit different in the turf industry compared to ag because one, we're not flat, typically flat throughout. We have a lot of topography, we have a lot of trees, so we have a lot of undulations, but we also we need more detail because we're more micromanaged, right? We're managing smaller areas. We're not just managing the whole, you know, these large agricultural fields. So satellites have somewhat of a limitation because of that, but nonetheless, there are data out there available, and it's typically NDVI. The advantage of satellites is there's historical data that you can pull up of your area so that you can see what your NDVI is in the past. And there's been some research, mainly in Italy, I believe, looking at NDVI on turf plots from satellite and trying to base fertilizer recommendations off of that, which can be questionable depending on kind of the details of the research, but nonetheless, it is still an option. And I'll talk a little bit more about using satellite data later. So just kind of a summary of all of these devices. The handheld ones are going to give you flexibility. You can collect data on the ground. You can collect in whatever frequency, sampling frequency you want, sampling interval you want. They can be somewhat expensive. The soil moisture sensors, in my opinion, pay for themselves after a period of time, even if you're using them on your greens, because I mean, those who are using it on their greens, I'm sure, are getting a lot of useful information on when to schedule irrigation. NDVI can be pretty expensive, the handheld version, but nonetheless, I think there's going to be some research that comes out. We're really still just trying to figure out how to utilize NDVI from a management standpoint. Like, how can we use the data to actually create some kind of useful, to determine when we need to do something from a management standpoint. And I think we're kind of getting there with some of the research that's coming out, or that's currently being conducted. And then time and labor is a big con because you have to go out and you have to walk a course or walk a large area to collect your data. And then not only once you have your data collected, you have to analyze it somehow, right? And that takes some learning. So it can be time and labor and costly. Drones, they're cool. You get quick data. They give you pretty good data, especially relative to a satellite, and they're getting better and better. I think the frequency of your data is a huge advantage. You can fly your course, you know, as often as you want, really daily, and some courses fly daily. And then you can really start identifying trends based on your management decisions, and then you can start modifying once you see how how things are reacting to the decisions that you're making. One of the cons is the minimal variable. You're typically only getting NDVI, NDRE, some kind of thermal. All of that's useful, but it'd be nice to also have some of these other variables too, especially soil moisture. In some cases, especially in my part of the world, salinity is really important, especially along the coast. And then cost. It can be costly to pay for the drones, just like any of these technologies that we're talking about today. And then satellite. Time is an advantage because you can typically just get online on the USGS website or some other website that offers satellite images. Sometimes it can be free, but typically the free ones are the limited resolution. So it typically, you would download it and it'll be in what's called a raster map, which is just a pixelated map. And if you download some of these free ones, maybe those pixels are very large, and you don't, maybe you only have like 4 pixels per fairway, and it's really hard to identify small areas. So the free ones can be, you can have the limited resolution, and then just like the drones, minimal variables, and definitely the resolution is the big thing with the satellites, unless you're paying for it, because there are some really good satellites there out now. Overall, with all of these technologies and everything that we've talked about today, is the learning curve. It's really, if you really want to do some of the things that I'm getting ready to talk about from a management standpoint with some of this data, you really got to sit down and figure it out. But once you figure it out, I don't think it's not too much. It's not much more effort after figuring it out. It's really easy to implement the data, and then to continue on some kind of program utilizing the data. I have a video here of a fixed thermal camera, Turf View. If anybody's familiar with Turf View, it's typically used on putting greens. Just another tool. I'm not going to show it here, but it's just another tool to consistently and constantly evaluate thermal on your putting greens, which could be useful for syringing and whatnot. All right, so switching gears. So that's just kind of a background to some of the technologies that I'm going to talk about here. And when I talk about golf course applications, so the big reason why we would want to do precision turf management on golf courses are to obviously reduce management inputs, but also to have a more environmentally sustainable approach to our management. So I'll talk about a few particular applications that I'm working on, and there are others out there. So I encourage you, kind of as we move into this data-driven management approach, to constantly be on the lookout at what other universities across the country are doing related to precision turf management. Sports field applications. I know that a lot of the folks on here are golf course superintendents, but I'm going to just briefly mention it. The advantages are the same as the golf, but a little bit smaller scale, obviously, unless you're at a really big soccer complex or some kind of baseball complex. But can it also improve athlete surface interactions, because you're in theory improving the uniformity of a field. So that's one of the areas of interest when it's related to precision turfgrass management for sports fields that my program is going to be looking at. And I won't get into those athlete surface interactions here, but I will show a couple examples on a sports field that could potentially be useful in golf as well. So one of the big things that I'm working on under the umbrella of precision turf management is this concept of precision irrigation. It's a USGA funded study that we started up in Minnesota I guess it was 2018 was when we initiated it. It's still ongoing. We had initiated it at one golf course, and then we moved to another due to winter kill. For the folks that are in Minnesota, I don't miss that. I was there for 2 years in 2018 and 2019. I don't deal with much snow anymore in Texas. So that's kind of nice. But nonetheless, we still have the ongoing study in Minnesota going, and we're hoping to expand a similar study to Texas. And the whole idea of this precision turf or the precision irrigation concept is to take some kind of GPS soil moisture device and go out and collect soil moisture data across your fairways. So one of the big misconceptions, and then use that data to schedule your irrigation site specifically. So you would initially start this by going out and walking your golf course and collecting soil moisture data. And that seems like a pretty daunting task, especially because a lot of golf course superintendents think that you have to do it periodically because it changes so rapidly. And yes, you're right. The magnitude of soil moisture will change very rapidly depending on temperature. But the spatial variability really does not change significantly unless you have some kind of construction project or something going on across your course. And what I mean by that is the wet areas are typically your wet areas and your dry areas are typically your dry areas. Now, the magnitude of that soil moisture might change, but unless you have your percentages adjusted on certain fairways, which most people do to a certain extent, or you irrigate one fairway more than the other one day, you're typically not good. Your wet areas are always going to be your wet areas because that's your underlying soil conditions, and your dry areas are going to stay typically your drier areas. So if you time your data collection correctly, which I typically recommend after a rainfall, whenever you bring your soil moisture up to near field capacity, you have that uniform application of water, so you're eliminating any kind of deficiencies in your irrigation system when you collect your data. Then you go out, you collect your soil moisture at that time, and you have this nice map from near field capacity conditions that will really highlight your underlying soil conditions. So maybe your light areas show up dry because you have a higher sand content, or maybe you have lower water infiltration in those areas. Your wet areas show up because you might have a little bit more clay content, or it might be, it might be the elevation might be lower, so you have water going to those areas. So if you time it right, if you collect your data, and this is based on our experience, there's no formal study that's been done, but I've collected data on a lot of golf courses over multiple months, and the wet areas do not typically change from month to month, at least. And even with the courses we've done year to year, wet areas are typically the wet areas, dry areas are typically the dry areas. Now, with that said, there can be some kind of small variations throughout, but that's just generally speaking. So if you go out, collect your data after a uniform rainfall near field capacity, then you can have a soil moisture map that looks similar to this. You could use your GPS soil moisture sensor to georeference the irrigation heads, which are these white dots. And then you can use this information for really several things. Identifying any kind of scheduling where you may need to adjust percentages of individual heads, if you have individual head control, to go up or down based on the surrounding soil conditions. In-ground soil moisture sensors is another big thing. A lot of folks will use them in putting greens, but expanding it out to the fairway it can be a pretty big task because, where do you put these things? But you could use a soil moisture map similar to this to try to maybe identify where to put that, where to put those across your course. One thing that we're pushing with this whole idea of precision irrigation, though, is to create boundaries, or we call them irrigation management zones, around individual heads. So if you have individual head control, you can essentially assign a class, a soil moisture class, to each head, and then program your system to irrigate based on their soil moisture class. So this is just an example of 5 soil moisture classes or 5 irrigation management zones. And then you could go in, you could selectively pick areas within each of these soil moisture classes to put in-ground soil moisture sensors that you can use to collect rapid data. Instead of having to go out and collect the handheld data, you'll have a representative in-ground sensor, or maybe even multiple in-ground sensors per class, that you can start creating thresholds for that class. So if you have individual head control, you can program your system for example, all the heads with a wet soil moisture class, program those to irrigate together, and then do that for each of these soil moisture classes. And then once you've reached a certain threshold based on the in-ground soil moisture sensor for that class, you only irrigate those heads that night. So it removes the chance for overwatering. So in theory, you're probably going to irrigate your drier areas more than your wetter areas. And in some cases, especially up in Minnesota, the couple courses that I've been at, sometimes your wet areas don't dry out. They can in certain parts of the summer, but sometimes the wet areas stay wet. So there's really no reason to irrigate them. So going back to the adjusting irrigation heads up and down percentages, that's a really good starting point. But with this tactic, it's really just eliminating the fact of doing the blanket application. You're only irrigating certain parts of the fairway rather than the entire fairway. So this is just an example of in-ground soil moisture sensor that we're using in a study that we're conducting up there. So we placed each one of these sensors within a soil moisture classes that we created on one golf course. We're currently doing it on one golf course. And then we're using, this is just an example of one fairway where we have 3 sensors. We created 3 soil moisture classes. We have one that's a wet class, a moderately wet class, and then a dry class. So the wet one's this top one, the moderate's the middle one here, and then the orange one is the dry class. So this is just an example of, I don't know the date here, we probably did maybe like a 10-day dry down or something to determine our thresholds of when to trigger the irrigation for these particular zones. So we went out, we mapped soil moisture, we created the irrigation management zones, we strategically placed these in-ground sensors, and then we conducted a dry down with the superintendent. And then we let it dry down until he felt uncomfortable. So once he thought it was time to water, we stopped the dry down. We took note of what the in-ground soil moisture sensor, what that value was whenever he told us to stop. And that was kind of his threshold of, okay, we need to water. And then we used those in the study to trigger irrigation. And we compared this method of irrigation scheduling to an ET-based method where we took a deficit approach and replaced 60% of ET loss every 3 days, and then compared that to the superintendent. So whatever he felt, whenever he felt it was necessary. So this study was set up over 9 fairways at a golf course. We had 3 fairways with the precision irrigation approach, 3 fairways with the superintendent approach, and 3 fairways with the ET approach. And we had, over the course of last year, we monitored how much water each of those 3 fairways were getting. And we saved over 60% water relative to the ET-based treatment with the precision irrigation. And we saved around 45% relative to the superintendent. And this was a pretty good superintendent too. And so it was pretty eye-opening to see how much water we were able to save on those 3 fairways taking this approach. So one thing that I always get from superintendents, less and less nowadays though, because I think people are starting to really adopt the technology, but early on especially was, I don't really need a soil moisture map to tell me where my wet and dry areas are. And so when I first got up to Minnesota, I kind of wanted to test that and to see if they really know their fairways and the soil moisture as well as they say they do. So I did a study where I interviewed 12 golf course superintendents in the Minneapolis area. I selected 1 fairway from their golf course and went out there. I took them where they took me to their fairway that I selected randomly. I didn't tell them which one it was before I got there. And I told them to draw, I had a boundary of the fairway, and I told them to draw their perceived wet and dry areas within the fairways. And so they did that on the sheet of paper. And then afterwards, I went out and actually collected the soil moisture data myself afterwards. And then I used that to compare their hand-drawn maps with the soil moisture maps. This was the best one, this image here on the left. This superintendent was obviously pretty good at identifying his areas. He knew he had a wet area up here at the top. He knew he was dry kind of here in the middle, wet towards the bottom. Oops. And then got dry again towards the bottom of the fairway. So he was pretty spot on. He was the best. Most people fell kind of within this range. They were kind of right and at the same time kind of wrong. At the bottom here, he knew he had a wet area, which he did, but he also had a dry area. Knew he had some kind of dry area here. Knew he had a dry area up here. And then there was really just one or two out of the 12 that just weren't even close. And this is an example of that. He thought he was dry up here, but he's actually pretty wet. And then along this whole ridge on the right side, he thought was the wettest area, which it was to a certain extent, but it also had this really dry spot. So the main take-home message from all of this, after we did some statistical analyses to really determine if the areas that they identified were actually the wettest and the driest areas. And statistically they were, as we did our analysis. But the big thing, just visually looking at these maps, is yes, they were able to identify some dry and wet areas, but typically they were overestimated or underestimated from a size standpoint. And then they also just didn't account for other areas. So they might have accounted for one dry area, but they didn't account for another really dry area. So that was kind of the take-home message from it. But another take-home message was, even if you can identify the wettest and the driest areas in your fairway, the advantage of the data and the maps, and especially the maps, because the maps are colorful and they're nice, they're a good visual, but there's a value attached to those maps. And the value is the most important thing, because that's going to be what you use to create your threshold to do some kind of management decision. So you actually need a number to put with the maps or with your experience so that you know when you need to do something. All right, so switching gears. So Ken already did a preview of the GPS sprayers, so I won't go into too much depth with that. Individual nozzle control, big advantage, minimizes overlaps, sprays within boundaries, and then variable rate applications, which I think are kind of the next step with these things. I stole these slides from Aaron Johnson several years ago, and I continue to use them. If he's on here, maybe there's some updated slides you can send me. But nonetheless, this is their Geotech program. This is going back to the satellite data. So this incorporates some historical satellite images of a golf course. You can really pull in however many historical images you want. You can incorporate a drone image if you'd like of NDVI, and then create these prescription spray maps. So in this particular case, this is a fungicide prescription map where you might have two zones. And this is just a really simplified example where one zone's getting one rate and the other zone's getting another rate. And then, as Ken showed in his presentation, you just drive this fairway as you typically would spraying. If you have a GPS sprayer, you can go faster. And as you transition into the different zones, then the rate will change based on whatever zone it's in. So if you were to expand that to an entire golf course, you could have a lot more zones. In this particular case, they combined a couple of these zones here on the left to create 4 different spray rates. This is for dollar spot control, where they have no rate at all, a lower rate, kind of a medium rate, and then a higher rate. And you can use that NDVI data, which the whole basis of this was looking at the historical images. Dollar spot could have affected NDVI. So you can identify maybe the lower NDVI areas might be the most susceptible to dollar spot, which is why you could spray those at a higher rate. Whereas the higher NDVI could maybe be less susceptible, so you could either not spray it at all or you could spray it at a low rate. The important thing about these maps and all maps that I talk about is to have that superintendent knowledge incorporated with them, right? So they can, you don't just go solely off the data. The data is not going to steal anybody's job. It's really using the data and your experience to create and modify these maps to make it applicable for whatever your situation is. So kind of sticking to the lines of variable rate fungicide applications, I'm doing a little bit of work with Virginia Tech right now. They've been a leader in spring dead spot research. They're currently looking at kind of really understanding why outbreaks occur in certain environmental conditions across a golf course. They're using drone images and some computer, some machine learning with some digital images collected from a drone to identify spring dead spots within a fairway. And the whole idea is to create some kind of hotspot map. And in this case, it's a spring dead spot. And where the red areas are the higher outbreak areas, the yellow areas, kind of moderate outbreak, and then the green areas are low outbreak. So this particular research has been focused on, and they have done research looking at variable rate for spring dead spot, but this particular research is really looking to see what kind of environmental and soil conditions are causing these outbreaks. But the end goal, I think, with some of this technology is to figure out how to incorporate these types of maps into some kind of variable rate spray for fungicides. Similar work's being conducted in Nebraska with fertilizer. My program this year is going to start focusing on wetting agents, not for golf, but for sports fields. And the reason for that is for soil moisture drives a lot of surface properties that are important in athlete surface interactions on sports fields. So if we can spray wetting agents, either blanketly or a targeted approach or a variable rate approach to improve the uniformity of soil moisture across the sports field, can we improve the predictability of that surface as an athlete plays on it? So there's a lot of opportunities for the GPS sprayers, and it's really just figuring out right now, one, the return on investment of this type of spray program, two, the efficacy of it, does it actually work? And then three, how can we make it as simple as possible so that you all aren't walking your entire golf course and collecting data by hand? And I think all of those things we're kind of working towards slowly but surely. Blanket aerification applications. I won't go into too much depth. This is the same football field. We collected data during every week during a football season on a native soil, natural grass field. This is penetration resistance, so the amount of force that it takes to penetrate into the surface, which is an indication of soil compaction. Kind of going back to my point about soil moisture, especially on a native soil. Penetration resistance, soil compaction. This is a field that receives blanket aerification. We collected data weekly for 3 years, and I don't have the 2016 data in here. Every time we made some kind of soil compaction map, the northern part of the field here was always the hardest and the most compacted area of the field. So it really raises the question, if we were to focus our aerification a little bit more towards these higher compacted areas, could we potentially over time improve the uniformity of soil compaction across the field? All right, so just to kind of wrap up here, limitations and barriers to adoptions of all of these technologies. This is going to be a focus of some of the work that I'm doing here in the next couple of years. We hope to be doing a survey hopefully later this year to really understand if you adopt some of these technologies, why, and if you don't, why not? The biggest barriers that we've identified through the few studies that have been conducted is obviously, and they're all somewhat obvious, the cost and the time, the training and experience, really learning something new, and putting the time into learning something new can be difficult for a lot of people. Lack of consistent protocols. There's really not any straightforward protocol currently available for a lot of the things that we do. And then even if you can go out and collect your data, there's really not any kind of, and we're getting better, but there's not some kind of universal decision support system. And there's actually there's a couple softwares that have came out recently that I think are going to really help. The Greenkeeper app obviously being one of those, but they need to be turf specific, and ag is getting pretty good with their precision agriculture, but it's specific for ag. We need our own decision support system that's specific for turf, because we're obviously a lot different than ag. And then I think the big thing, and this is kind of our neck of the woods in the university setting, is to do the research to determine the criteria to assess the benefits. Is it worth doing? And if we see the benefits of some of these things, how can we then develop these better decision support systems to more entice adoption of these technologies? Going back to the irrigation study, 60% that I talked about, 60% water savings, or even 45% water savings that we saw. It's really nice, but the work that it takes to set that up is a really big hurdle. And I'm not naive to the fact of that. There's a lot of work that goes into going out and collecting the data, setting up an irrigation system, continually monitoring soil moisture sensors in the ground. It takes a lot of work, but based on conversations with superintendents that I've had, and I'm sure others that are speaking have had, once you do it one time, or you spend a little bit of time doing it, it just gets easier and easier, and you're really able to fine tune and refine your program, your precision program, to really see the benefits. It's just a little bit of upfront cost and time that you have to invest. So with that said, I have developed, knowing that there's a limitation with the protocols. When I was in Minnesota, I did develop a golf course soil moisture mapping protocol, which is the one on the left. You can download that. I'll show a QR code here in a minute. You can download that and incorporate it into your program at your golf course, as long as you have some kind of GPS soil moisture meter. It's a step-by-step tutorial. It's a 20-page document, but we did 4 or 5 minute long videos on each section, which would equate to maybe 50 minutes of videos. And it'll show you step-by-step how you can go out, collect your data, analyze your data using a free software, and then spit out this final map with the soil moisture classifications. And that's really a baseline. It's not the end all be all. It's the baseline to get you to try to program your system to irrigate a little bit more site specifically. And you can modify it as you see fit using that baseline map. And then if there's anybody on here with sports fields, we did a very similar one for sports fields to map various surface properties on that. So if anybody's interested in those, you can just pull your phone out and take an image of these QR codes. And that's really my last slide, so I'll just leave this up to give folks time.